Today we want to talk about DSC, especially our chip DSC system with our new low mass sensor. This year I already hold a lecture regarding our extended sensor, and now there's a third option for our measurement systems for the chip DSC. So that's me. So I'm product specialist for calorimetry here at Lindsay. I've studied automotive electronics in Zwickau, Germany, and I'm working for Lindsay since 2017. And yeah, if you want to get in touch here, you can find me on LinkedIn, on Xing, uh, and of course you can write me a mail. So this completely depends on you. First, I want to tell you something about Lindsay's Messgeräte GmbH itself. So we were founded in 1956 by Dr. Maximilian Lindsay here in Selb, in Bavaria. And so we still manufacture our products here in Selb. And yeah, but there are some other subsidiaries in China and in USA. And of course, we are acting worldwide with more than 65 traders. All in all, we produce measurement instruments for thermal analysis. And of course, in our own lab, we also do some service measurements. So on the right here, you can see Dr. Maximilian Lindsay's, Klaus Lindsay's, and our current leadership, Florian Lindsay's and Dr. Vincent Lindsay's. So our product range, of course, we have some DSCs here I want to talk today. But there's also thermogrammetry, STAs, so simultaneous thermal analysis. So they combine DSC signals with TGA signals. Of course, we have dilatometry, thermomechanical analysis, thermal conductivity and thermal diffusivity, some analyzers for thermoelectric materials, thin film analyzers, Hall effect, and so on. And of course, we also do some special instruments for special applications here. But all in all, today we want to talk about DSC, so the differential scanning calorimetry. Here I want to show you the special thing regarding the chip DSC. So on the left here, you can see the classic way how a DSC works. So we have a surrounding oven with the heater, of course, and inside this oven you can find a sample crucible with the blue sample and a reference crucible with a reference material. Sometimes you use a material here, but often this crucible is empty. And below these crucibles, you can find your temperature sensors. And the difference leads to our DSC signal here. With chip DSC, now we've converted this. So now there's no surrounding oven. The heater is internally at the moment. And on the top, you can find the temperature sensor for the sample and, of course, the crucible for the sample with the sample itself. And below this heater, you can find the reference temperature sensor and the fixed reference at the bottom. So I've prepared another picture from the literature. This is how a DSC normally looks like or normally works. So all in all, we are measuring the heat flow here. So the temperature between sample temperature sensor and reference temperature sensor. And this way we receive our DSC signal, so the heat flow signal. The losses are compensated by the reference crucible or the reference at all. And the difference here leads to our signal we can see later on. And now here you can see on the left another picture of our chip DSC sensor, how it normally works. So in the mid, you can find the heater, at the top, the sample temperature sensor, and at the bottom, the reference sensor. This complete sensor is made by thick film technique. So we are using LTCC ceramics here for the sensor, and everything you need for a measurement is inside this small sensor. So now let's talk about what do we want to measure at all with our DSCs. So with conventional DSC measurements, they are used in industry, teaching, or research. It never doesn't matter here. There are some transitions we could detect. So at first, there's a glass transition, the glass point, maybe with a relaxation. And after this, you can find, for example, a cold crystallization. By the way, the example here at the right is a polymer with all the transitions we could find here. After the cold crystallization, we can find the melting, of course, and at higher temperatures, it could lead to oxidation or thermal degradation. So this depends on the atmosphere you're using. So on the one hand, you can find the oxidation if there's some oxygen there, of course, or the decomposition if there isn't anything like this. And of course, we also can detect the cooling scan. So also there we receive some information like the crystallization or the glass transition here. Sometimes these phenomena are also overlapping. So for example, the glass transition here is overlapped by the relaxation there. And yeah, sometimes this leads to some problems or issues, but of course there are some solutions we can offer here. So now you can see our small sensor here. So there are currently 3 different versions. So we produced and tested several types of these sensors, and what you can see here in the first picture is all of them are compatible with our sensor holder, so you can use them in every chip DSC you want to. For example, if there's already existing system from Lindsay, so of course you can use our different sensors here. So let's talk about theoretics. So what could we achieve through the different sensor types? So the first thing is, of course, sometimes for some investigations, we need a higher sensitivity. And for this reason, we thought about it. Okay, how could we adjust these sensors for better results for special investigations? So here you can see the principle of our extended sensor. And the thing is, the DSC signal is defined by the temperature difference between the sample temperature sensor and the reference temperature sensor. And if this difference gets bigger, for example, through a bigger sensor, also the DSC signal would be bigger, and this leads to a higher sensitivity here. So we achieved a higher temperature gradient between sample and reference, and this way we receive a bigger signal. The second thing is, what else could we do here? We could lower the thermal mass. The reason for this is sometimes we need some really fast transitions or a really fast measurement system. For this reason, we've lowered the thermal mass or the mass of this sensor at all. And for this reason, we've lowered the height of our sensor here. So the mass and the thermal mass of our low mass sensor I'm talking about today is just smaller than the standard one. And for this reason, it should be a bit faster. But we will see this in the results later on. And here we go for the results. So what we can see here is the signal height differs between the different sensors. So the black curve you can see here is our standard sensor with the normal height. And the red one is our extended one with much more signal, so 38% more signal in comparison to our standard sensor. And due to the smaller design with low mass sensor, we receive less signal in comparison to our standard sensor. So the sample we've used here was indium. It was the really same sample, heated up with 10 Kelvin per minute in our standard crucible, and just a common atmosphere. It was just air. Maybe you're wondering, why do I show the DTA signal here in millivolts? The reason is, if you calibrate your device for enthalpy, the signal height would be the same here, and the differences between the sensors aren't that good visible. So this is the reason why I just showed a DTA signal without any enthalpic calibration. So the next thing we want to talk about is the time constant. So here you can see why the low mass sensor is the best option for fast transitions and really fast measurements. So with the extended sensor, of course, there's more terminal mass, and the time constant tau is much bigger than the standard one. So the standard one has a time constant of 1 second under the given measurement properties, and the extended one receives 1.6 seconds. But with our low mass sensor, we could achieve 0.2 seconds faster time constant with this sample, and so it's faster here in this case. By the way, if you're wondering how this tau is calculated, so this is the time between 90 and 10% of the peak after the peak maximum. So here in this case, at the right side of your peak, you check where's 90% of my maximum peak height and where's 10%, and then you measure the time constant here. By the way, all of our signals here are raw signals, so there's no mathematical correction or something like this. So like other manufacturers do sometimes. So these are really the raw signals, and these are the raw values for peak height and the tau, of course. So let's check another example here. So for example, yes, we want to calibrate with indium, tin, lead, or zinc, or whatever, any given metal. But all in all, your investigations aren't that easy mostly, I think. So I've checked these sensors also with our reference material. It is PET. So I just put in a complete granule and heat it up with 25 Kelvin per minute in our standard crucible under normal air conditions. And what could we see here? At first, at around about 80 degrees, we can find the glass transition. At around about 150 degrees, you can find the recrystallization here. And the melting starts at around about 230 degrees Celsius. And now, what could we see here? Maybe you can check the y-axis here. So again, I'm showing the DTA signal because I want to see the difference in the sensitivity here. So the standard sensor with PET is the reference in our case. And what we can see here, especially at the glass transition is much higher here in comparison to our standard sensor. And what we also can see, we know that the low mass sensor has a bit less sensitivity in comparison to our standard sensor, or especially to our extended sensor here. But that's not the topic of our low mass sensor. The strength here is the fastness of this sensor. So let's compare the layout of these sensors. So this is the standard one with the internal heater references and the crucible. So this is the most universal one for the really most applications. So until now, all systems are sold with this standard sensor, and it's the really best compromise between the signal height, so the sensitivity, and the time constant here. So it's pretty fast, much faster than many other products here or conventional DSCs, but with an also really good sensitivity and a good signal. Just an example here in this case, this is a PET measurement with two different heating rates. So at the top, you can see the heating rate of 20 Kelvin per minute. This works pretty well with our standard sensor, and also with 15 Kelvin per minute. So for convection reasons, the heating rate of our chip DSC is mostly a bit higher in comparison to conventional DSCs. And yeah, between 20, 50, or 100 Kelvin per minute, this is the heating rate range you should use the chip DSC. Of course, it's possible to use much higher or much lower heating rates, but that's common practice here to use around about 50 Kelvin per minute. So the next thing is our extended sensor here. So you can see it here. There's also a bigger reference at the bottom, and this leads to less convection at the bottom, so at the reference side. And for this reason, also the noise is lowered a bit. And of course, also we can find the 38% more signal here for the sensor. So, for example, this works perfectly for some slower investigations. For example, polymers at lower heating rates, for example, 10 Kelvin per minute or 5 Kelvin per minute. So I have an example here with different heating rates with our extended sensor for ABS. So with 20 Kelvin per minute, what's common practice for 10 Kelvin per minute, and with 5 Kelvin per minute. And just to comment, for 5 Kelvin per minute, the standard sensor, or especially the low mass sensor, wouldn't work that well in comparison to our extended sensor, because here we can find a bigger reference, less convection, and all in all, a better signal height here. So what could we see here in this slide? Of course, okay, the glass point temperature is changing with the heating rate. And this is important to know if you want to compare your measurements with other devices or with other samples. You should really make sure they are using the same heating rate and the same properties at all. So there's a difference of from 91 degrees Celsius to 104 degrees Celsius. So the differences could be really big here. But what we also can see, the height of the glass transition gets higher with higher heating rates. So higher heating rates are better sometimes to see smaller transitions here. This is pretty important to know. And last but not least, our newest sensor is basically our low mass sensor. I already explained the layout. So we minimized our LTCC layers here for the smallest time constant. And of course, there's also a smaller temperature gradient, and this leads to a bit lower signal here in this case. So just an example, why do I need the low mass sensor? Then because normally, of course, we want the highest sensitivity we could achieve, but sometimes there are some investigations, they are pretty fast. So for example, we have a mixture of polyethylene and polypropylene here, and now we want to figure out the difference of this mixture. So I run the sample with different heating rates, and the thing is, if you run the sample with higher heating rates, both peaks of these polymer are combined more and more because the time constant of your measurement system is too high. So, and why should I use such a high heating rate? This depends on your application. For example, if you're focusing on industry or something like this and want to compare different production properties, it could be important to use such high heating and cooling rates here. And so for this reason, it could be important to run it with 60 Kelvin per minute or even higher. And what we can see here is also at 60 Kelvin per minute, the peaks could be evaluated, it's possible to separate them by our software. And with lower heating rates, it's get much clearer and much easier. So for this reason, the low mass sensor is perfect for close transitions, for several peaks or overlapping transitions like glass transitions and meltings that are near to each other on a temperature range. But there are some other advantages through our low mass sensor because we've changed the layout at all. Maybe you recognized it the slides before, but now there's no more positioning border. Okay, the positioning border is a good thing. It makes the crucible positioning on the sensor much easier. But through this flat design, we could measure some more samples here. And of course, the mass is lowered, and for this reason, it's easier to see these fast transitions and get a lower time constant. So for example, you have to use another crucible that's not sold by Lindsay, and wherever you can find this crucible, you have to place it on your device. So for example, you can see this fused silica crucible here, and it just doesn't fit to our standard sensor you can see at the left. On the right, there's no positioning border, so there's no problem to use this crucible for your investigation. Another point is what happens if you have to measure your sample directly because it just doesn't fit to any crucible you have in your lab. So at the left side, you can see our standard sensor again, sorry. And on the right side, our low mass sensor. And at the left side, you can see, okay, the sample is just placed on the positioning border of our sensor. On the right side, it would work because there's good contact between the sensor and the sample itself over the complete range of our sensor here. Of course, you can also use a crucible here. So if you don't have any crucible for your sample, it's possible to place it directly on the sensor. But of course, you can also just use a small plate of aluminum, and it works good also. You can see here in the right. So it's just a plate of aluminum to avoid contamination of our sensor here. So, of course, now there's the question for those who already use a chip DSC, are the new sensors compatible with our old systems? And I can say, yes, I already mentioned in the beginning, all of our sensors fit to the old devices. And yeah, it doesn't matter if you want to buy another low mass sensor or an extended sensor, all of them should work with your existing system. And of course, they also work with the system you want to buy in the future. And what's also important, do they fit to all our additional options here? And yes, they really do. Just for those who use a chip DC100, you can see it in the lower right here. We have to exchange this cooling frame for our cooling options, but all other cooling options and so on are compatible with this system. And of course, if you want to rebuy a sensor with the existing system for your existing system, you will receive also this cooling frame for free here in this case. And what's also important, of course, all our other systems we sell and additional features like Raman spectroscopy or UV light curing option or video option, different cooling options we offer, and so on. All of them are compatible for the different systems. So it doesn't matter which system you've already bought or you want to buy. All chip DSCs are compatible with our 3 different measurement cells because everything you need is inside this sensor. So there's an internal heater, there's a reference sensor, and there's the sample sensor inside this crucible. inside the sensor, sorry. So just a short conclusion. What's important for the chip DSC all in all? The sensor is exchangeable by you, so there's no need for any Lindsay's worker. It's really plug and play. You just have to open the frame there, and then you can place the new sensor inside. So it doesn't matter if they're broken or not, or you just want to clean them. So it's pretty easy to exchange the sensor, and also to calibrate. The calibration just lasts, for example, at 15 Kelvin per minute. So it's just 15 to 20 minutes, depending on the samples you want to calibrate with. So it's pretty fast and easy to use. What I'm talking about today was the customizable sensor selection here. So regarding your application, we have different sensors for your needs. So all in all, it's our standard sensor. This was the only sensor we sold until now. And now there are two more options, the extended one for a higher sensitivity and the low mass sensor for a lower time constant and faster measurements. And I already mentioned the slides before. They are compatible to all our measurement systems, of course, for chip DSC and also to our additional options. And yeah, so this could be important if you have an investigation that probably doesn't work at the moment. And so, of course, we can discuss if there's a better option for your investigation regarding our sensors. And what's also important, I think so, the marketing told me, so it's a fairly priced measurement system. So for example, you're working with explosives or something like this, or with corrosive materials and atmospheres, it's pretty easy and not so expensive to exchange the sensor, and it's really easy to exchange the sensor itself and recalibrate the device here. So all in all, it's a pretty fairly priced measurement system and also device at all. What's important for many customers of us is there's a really high sample throughput, because a standard measurement, for example, for PET with 20 Kelvin per minute, just lasts 10 to 15 minutes with your with sample preparation, because the cooling of the device is pretty fast. So it just lasts around about 4 minutes until you're near room temperature again. With conventional DSCs, you often have the problem you have to cool down for minutes or 4 hours, for example, because they are really big with really big ovens. And that's another point. The footprint of our chip DSC is pretty small. So it's for the chip DSC1 and chip DSC10, it's 20 per 20 centimeters. So I think you will find a place in your lab here. And the ownership, is low cost at all. So I think this device is pretty affordable. So that's the point at all. That's what I can tell you currently about the chip DSC sensors. And what's now important for us, it would be perfect if we can go for a discussion right now. If you have any question, of course, you can ask them directly, but also if you have some applications you're interested in for the different sensors, please feel free to contact me personally or maybe also here in the chat. And yeah, many thanks to all of you. It was a pleasure, and yeah,